electrolytic cells is the last part we have to do about redox reactions. And we actually did it the other way around when we did it in class. And we did this in a lot of detail because, as I said to you, if you understand it the one way around, you understand it the other way around as well. Just remember that in an electrolytic cell, the energy conversion is now electric energy into chemical energy. So there's going to be chemicals that undergo a reaction because you are adding energy. So it's going to be a non-spontaneous reaction because it doesn't happen spontaneously. Electrical energy needs to be supplied. The anode and the cathode will still be exactly the same. The oxidation half reaction would still be the one that you find highest in the table because the strongest reducing agent would rather be oxidized. The stronger oxidizing agent would rather be reduced. So you're going to follow the same procedure. You find all your substances. The one highest on this side is the strongest reducing agent and therefore would rather be oxidized. The one on the bottom, the strongest oxidizing agent, rather be reduced. Please, that sentence is super important. I cannot repeat it enough times. So, an electrolytic cell, you're going to always see a battery. So, we cannot use alternating current because that will have electron going and coming and going, coming and going, and we don't want that. So, you're going to have an electrode still, but this time they are actually connected to positive and negative sides of a battery. So, you should remember that the long one is positive, the short one is negative, and then we're going to have ions swimming around. So again, you're going to find your ions that are swimming around. One would rather be oxidized, and that will be your oxidation half reaction. So oxidation, remember, is giving off of electrons. So oxidation will happen at the positive one because at the positive one, electrons will be given off. A reduction is gain of electrons, and the negative one would be the one that where something can go and gain electrons. So that will be our cathode. So let's write that down. So the positive one, if you look at it, there will be some negative ions or something swimming around here. I'm going to let's use NaCl because it will make our explanation later easier. So chlorine ions would go there. This is if I've got molten NaCl. So there's no water yet. So there will be molten NaCl. The negative ion will go there. If you go and look at your reaction, I'm just going to increase the size of our table quickly. If you look at your Cl minus ions, they are there. I don't have anything else. So that means I'm going to have the Cl minus give off 2 electrons to form Cl2 gas. And that's going to be your half reaction that you write down, oxidation half reaction. Because it's oxidation, we know that oxidation happens at the anode. So therefore, we're going to name this side the anode. The Na plus ions, remember, you need to dissociate the ions. The Na plus ions are up here. There's nothing else in competition here. So it is the only oxidizing agent, so it will be reduced. It will take up ions and electrons and form sodium ions. So reduction happens here, and that will then be the cathode. So that's the basics of what happens, is that the negative ion will move to the positive ion will move to the negative. But then there are other substances sometimes. Remember, if you see water or if you see AQ, then very different things can happen. And then you need to account for water as well. And I'm actually going to just look at this reaction because then it will help us with the application as well. So water will become part of the competition. And you need to now look at water in a little bit more detail because now if I have water in this reaction, for instance, I need to remember to go and highlight my water. So I've got sodium there. I've got water. Remember, that's the water I use because all the other ones need something else. I've got chlorine ions. I don't have chloride ions. Remember to call it the right thing. I don't have chlorine. I have this water and I have the water just above chlorine there. They're very close together and you must note that because it's quite important. So if I'm going to find my oxidation and reduction half reaction, I'm going to look for my strongest oxidizing agent because that will rather be reduced. And you will see that that would be my reaction. That will be my reduction half reaction. You will see it's a non-spontaneous reaction because they do not give you a positive gradient and you will actually get a negative E naught value. That's the amount of energy that I have to supply then for this reaction to take place. Now I'm going to look at the strongest reducing agent because the strongest reducing agent would rather be oxidized. So if you look at your two half reactions that should be taking place, it is water that will form hydrogen, and it's water that will form oxygen. That will be our two reactions under standard conditions. And that's how you deal with anything. So if you forgot how these cells work, please go and look at the video again. There were quite detailed videos on this. So go and have a look again. But the procedure, exactly the same as what we just did for galvanic cells. You find your strongest reducing agent, that will be your oxidation half reaction. You find your strongest oxidizing agent, that will be your reduction half reaction. Exactly the same. Now, please remember, if we are not at standard conditions, and this is what you need to now remember, and the main one that we deal with for that is chlorine. Because if I have a solution, now remember standard conditions, 1 mole per cubic decimeter concentration. Now if I look at the water that I just had there and the chloride ions, if I increase the concentration of my chloride ions, I make it a stronger reducing agent. So that means it will move a little bit higher on this table. This only happens when they are very close together. So you will see in the chloroalkali industry, we work with concentrated Cl minus ions. So that we call brine. We'll look at the applications quickly, but again, you've got videos for each of the applications. So the chloride ion is more concentrated and therefore becomes a stronger reducing agent and therefore would rather be oxidized than the water. So please remember that the standard rules only apply at standard conditions. And if the concentration changes, it will change our standard conditions, and then you need to keep in mind that different reactions might actually take place. All right, let's look at our points. So we know how to identify the anode and the cathode because anode is still where oxidation takes place, cathode is still where reduction takes place. The anode would normally be the positive one because oxidation is where electrons are given off, and that would normally happen at the positive electrode. And the cathode would normally be the negative one because electrons can be gained there, which is reduction. Now, half reactions you can write. Please remember that there's one half reaction that's not given to you, and it's actually mentioned here for aluminium oxide. If you have aluminium oxide, you have Al2O3. Now, if I split this up into ions, I have Al3+, and you'll find this on your table, and that will be Al3+, will take up 3 electrons, and I will form aluminium. So that half reaction is there. I'm not going to make it bigger again. It's there. And I'm going to form aluminium. So that's going to be my reduction half reaction because I'm gaining electrons. Now, if you look, and this will move to the negative electrode, remember? And reduction happens at the cathode. So it all makes sense. Oxygen will form an O2 minus ion, and this is the one that's not on your redox table. A O2 minus ion, and that is going to form oxygen gas for us. So O2 gas. Now, if you look at it, I need 2 ions to form an A2. So I need 2 of these ions, and that means that 2 of these ions will have to give off 2 electrons each. So I'm going to end up with 4 electrons that are being given off. Please remember this half reaction you need to learn or just make sense of it. It is not on your redox table. Writing the overall ionic cell reaction is exactly the same as it was in galvanic cells. The oxidizing agent and reducing agent is exactly the same. So here, this is my reduction half reaction. So this will be my oxidizing agent. This is my oxidation half reaction. So this is my reducing agent. The same way. Now, for electrodes, often with the electrodes used, we don't want the electrodes to actually play a part in the reaction. So for the electrodes, we often use something that's inert. What that means is that it doesn't really react. It's not reactive. So something like platinum. Also, if we have gases forming, platinum will catalyze the reaction. Graphite is a nice one to use because it doesn't interfere with my reaction either. And it's all of these are very good conductors of electricity, and therefore we can use them. We've spoken about the concentration. Normally, you would follow the rules. The highest one will be the strongest oxidation reaction, strongest reducing agent, and the lowest one will undergo reduction. But if the concentration change, please remember that there could then be a different reaction happening because of the becoming a stronger reducing or oxidizing agent. Now, we need to look at the applications of electrolysis quickly. So I'm going to go through them fast because you've literally got videos for each one of these. The applications, the first one is copper chloride. This is just copper chloride, gold chloride. That's basically plating. So if you want to plate something with a metal, please remember that the metal ions are always positive. So if I have my metal ion, whatever it is, I need to, and I have a spoon that I want to cover in that metal. I need to connect that to the negative side of my battery. Please remember that. And that's the short one. Now here it will gain electrons, so it will always be reduction. So you're going to connect the thing that you want to plate with the metal as your cathode. Always. And on the other side, you just need something that can conduct electricity. Now in plating, so this will all be in an electrolyte. And remember, there will be some negative ion. This can be nitrate, it could be chloride, it could be our spectator ion, something that doesn't take part in the reaction, like SO4 2 minus. But now, this could be anything. This could be carbon, like I said, graphite, it could be platinum, it could be anything that doesn't take part in the reaction. But what's clever is if you use something that will form M ions. So if this is metal M, and I can take that metal M and form M plus ions and give off electrons. That means the oxidation half reaction will give me some M plus ions, and the reduction half reactions will form the M on the other side. That will help replenish those ions, and I will be able to have a better plating reaction happening. There are lots of examples like this. Now, in copper refining, it's basically the same principle. This here, where I have my oxidation happening, will be my impure copper. So that means I will form copper, and those copper ions will go here, and I will extract the pure copper. But just remember that there can be other things mixed here with the copper, and then you have to go and look at your table. And again, this is where those sentences come in very handy. Because then what you're going to say is if you have, for instance, copper in competition, let's just quickly look here. There's, for instance, cobalt. Let's just look at cobalt. And there's copper. Now, cobalt might actually undergo oxidation and form cobalt ions. So those ions will be swimming around, and you can even have aluminium, and those ions can be swimming around. So they can be oxidized, and then the copper will also be oxidized. So you can have all those ions swimming around. But then if you look at the oxidizing ability, so the strongest oxidizing agent, it will still be copper, and therefore copper will be plated. So the sentence that I said, you're going to say that copper is the strongest oxidizing agent and therefore would rather be reduced to form copper metal than all these other ions. Okay, so please remember that. If there's something like gold, those normally just fall down to the bottom as rubbish or sludge. So that's the copper refining. Now, sodium chloride is the big one. There's three different cells, and you need to know the chloroalkali industry has the membrane cell, the mercury cell, and the diaphragm cell. Basically, they are the same reaction, and they just use a different method of forming the chemicals for us. And the chemicals that they're forming for us is chlorine gas, hydrogen gas, and sodium hydroxide. So please remember that it all happens with brine. Brine is NaCl in water, but it is concentrated. So it's exactly the reaction I showed you earlier. So, not that earlier, not much earlier. If I look here, I have my Na plus ions, I have water. And you will see that on this side now, water is the strongest oxidizing agent and therefore would rather be reduced. And that is our reaction that takes place is our reduction half reaction, and that's our cathode reaction. If you look at your oxidation half reaction, you will have Cl minuses, you will have water and water again. So water should happen under standard conditions, we would form oxygen, but because brine is concentrated NaCl, the chlorine will have a little bit of a stronger reducing ability, just enough to make it go above the water, and therefore I form chlorine gas as my other product and not oxygen gas. Please remember this because they do ask it. The sodium and the water is too far away from each other for it to have an effect there. It has to be very close to each other on the table for the concentration to actually play a role. Now, the other product, you will see here, I formed some OH minuses and I had my Na plus ion swimming around. So I actually form as my third product NaOH, which is still a solution. And that gives me my three products, hydrogen gas, chlorine gas, and sodium hydroxide. But you need to go and look at the videos of those three cells in detail and make sure you know which one is the best and which one is the worst. We don't really use the mercury cell anymore, but the mercury cell also, the sodium ions there actually go and dissolve in the mercury. And therefore, the sodium ions will actually be the reaction at my cathode and not the water. So you also need to note that in the mercury cell, there's a different reaction taking place. Aluminium, I've already mentioned. We don't use aluminium AQ because you will see that if we did, the aluminium, let me just clean up a little bit. If you were using AQ, you'll see aluminium is here and water is here. So I would never form aluminium because the water would be the strongest oxidizing agent and therefore I would form hydrogen gas. So I can't use AQ or solution of aluminium. So they use molten aluminium oxide. And as I already mentioned, it's the aluminium the Al ion and the O2 minus ion. And you will also see that they use carbon electrodes. Now, one thing that you need to remember is that the oxygen that forms at the anode, because this happens at very high temperatures, the carbon and the oxygen will react with each other. So you'll have carbon with oxygen combining, and not a plus, not another something. It will give us carbon dioxide. And that carbon dioxide will leave, meaning that these electrodes will be corroded and you need to replace them regularly. So please remember that. And carbon dioxide is obviously bad for the environment. So yeah, they ask you some practical questions on this. Now, the last thing we need to do is looking at calculations. Now, again, there's a video that does this in a lot of detail. But what you need to read is the question is either going to give you information about your chemicals or it's going to give you information about your current. Now, remember, current means electrons. So if the question gives you information about your current, you need to find out how many electrons I have and bring that to your chemicals. So let's say Let's see. So let's say they tell you that you've got a current of 5 ampere. You're going to use your equation Q equals IT, and they should then give you a time, and you are going to use this to get your charge. Now, charge is electrons. So you need to go and figure out how many electrons you actually have. And to do that, you need to use your next equation, because Faraday's constant tells us the charge on 1 mole of electrons. So then you're going to use your charge that you calculated. You're going to use Q equals NF, and this would lead you to the moles of electrons. Once you have your moles of electrons, you're going to use your plain stoichiometry ratio, and you're going to say my electron ratio to my chemical ratio. Now, let's say we were using our aluminium reaction again. Remember, it was Al3 plus that took up 3 electrons to form aluminium for us. So here the ratio of electrons to aluminium would then be 3 electrons will give me 1 aluminium. So whatever your answer is here for aluminium, for your electrons, you're going to have to divide it by 3 to get to aluminium. Same as your normal mole calculation. So your moles of your aluminium is going to be a third of your moles of your electrons. Once you have your moles of your electrons, you can work out anything that they ask you about your chemicals. You can work out the volume. If you use N equals V over Vm, remember that's at standard temperature and pressure. You could use N equals M over Mr if they ask you for the mass of the aluminium that you produced. Easy, just use your mole ratio. If they give you the question the other way around, so they don't give you information about your current, you're going to follow a very similar method. Now, please go and do the worksheet again and practice this, because you do need to practice it a little bit. If they give you information about the chemicals, they normally give you the mass or the volume. So your first job is to take the mass or the volume and use N equals M over Mr or V over Vm and go and work out the actual moles. But remember, this is the moles of my chemical. So my moles of my aluminium will then lead me to my moles of my electrons, because you're going to look at your ratio again. So my ratio of aluminium to electrons here is 1 to 3. So to take me from my aluminium to my moles of electrons, it's going to be 3 times the moles that I need to do. So here, if I want my moles of my electrons, it's going to be 3 times the moles that I calculated for my aluminium. Normal stoichiometry. Once I have my moles of my electrons, then I can go and use these 2 equations, because these 2 equations only count for electrons. So now I can say Q is equal to NF from your information sheet. This gives me the charge. And once I have the charge, I can use this gives me my number it gives me my charge. And then I can use Q equals IT, and I can either go and work out the current if that's what they ask me, or I can go and work out the time. And that's it. Now all that's left for you is to go and practice these questions, looking at the past paper questions.